heading to the sixth topic of the chapter, colligative properties and determination of molar mass. So, what are colligative properties? Let us look into the text here. We have learned in section 1.4.3 that the vapor pressure of solution decreases when a non-volatile solute is added to a volatile solvent. There are many properties of solutions which are connected with this decrease of vapor pressure. These are relative lowering of vapor pressure of the solvent, depression of freezing point of the solvent, elevation of boiling point of the solvent, and osmotic pressure of the solution. All these properties depend on the number of solute particles irrespective of their nature relative to the total number of particles present in the solution. Such properties are called colligative properties. Colligative from Latin co means together, ligare means to bind. In the following sections, we will discuss these properties one by one. So, what is being stated here is that in the previous sections, we saw that vapor pressure of a solution decreases when a non-volatile solute is added to a volatile solvent, because at the surface, the number of molecules of the volatile solvent would decrease when you add one non-volatile solute into it. So, as the number of volatile solvent molecules decrease at the surface, number of molecules turning into vapor phase would also decrease, and the vapor pressure also would decrease. We have seen this in detail in the other section. So, there are many properties of solutions which are connected with this decrease of vapor pressure. Why there are properties connected to this decrease of vapor pressure? They are relative lowering of vapor pressure of the solvent, depression of freezing point of the solvent, elevation of boiling point of the solvent, osmotic pressure of the solution. All these properties. Now, what are colligative properties? This definition is very important. They might ask, what are colligative properties? All these properties depend on the number of solute particles irrespective of their nature relative to the total number of particles present in the solution. Relative to the total number of particles in the solution, these properties depend on the number of solute particles relative to the total number of particles in the solution, irrespective of their nature. In the sense, the solute may be of any kind, non-volatile, volatile, polar, non-polar. The nature of the solute does not depend here. Only the number of solute particles are taken into consideration for these colligative properties. That is why, such properties are called as colligative properties. Now, colligative from Latin means co means together, ligare means to bind. So, together bound particles, we are going to talk about their properties. Okay. Now, the first colligative property is relative lowering of vapor pressure. In section 1.4.3, we saw that vapor pressure of a solvent is in solution is less than that of the pure solvent. That is what, in the pure solvent, the vapor pressure will be greater than in a solution where there is an addition of non-volatile solute or volatile solute. Now, Raoult established that the lowering of vapor pressure depends only on the concentration of the solute particles, and it is independent of their identity. The equation 1.2.0 given in section 1.4.3 establishes the relation between vapor pressure of the solution, mole fraction, and vapor pressure of the solvent. That is, P1 is equal to Chi1 P1 naught. Now, before coming to that, we saw that there is a decrease in the vapor pressure when there is a solute added to the solvent. That is, vapor pressure of a solvent decreases in a solution than in its pure form, right? That is what we saw. Now, Raoult had found that this decrease is only caused because of the number or the concentration of the solute particles and not because of its nature. That is, whatever be the solute there, the nature of the solute does not depend, does not affect the lowering of the vapor pressure. Rather, the concentration or the number of solute particles present in the solution only is going to affect the lowering of vapor pressure here. So, we saw this relation between vapor pressure and mole fraction and vapor pressure of the solvent as P1. That is your one, we will always take it to be solvent molecule, right? So, P1 is the vapor pressure of the solvent in the solution, will be equal to Chi1, that is mole fraction, and P1 naught, that is vapor pressure of the solvent in its pure form. The reduction in the vapor pressure of solvent delta P1 is given as delta P1 is equal to P1 naught minus P1, which is P1 naught minus P1 naught Chi1, which will be equal to P1 naught into 1 minus Chi1. That is reduction in the vapor pressure. As we saw, this P1 is nothing but vapor pressure of the solvent in the solution. That means this P1 would be lesser than P1 naught. right? P1 naught is the vapor pressure in the pure form, in the pure component. Now P1 is the vapor pressure in the solution, so P1 would be lesser than P1 naught. And by how much has it decreased? To find that, we are finding delta P1. Delta P1 is nothing but how much reduction there has been in the vapor pressure of the solvent, in its pure form and in its solution form. So delta P1 is equal to P1 naught, that is the vapor pressure in its pure component, minus P1, that is vapor pressure in its solution. Now P1 we know can be represented by chi1 P1 naught, so P1 naught minus P1 naught chi1. Now taking P1 naught as common, we get it as P1 naught into 1 minus chi1. Knowing that chi2 is equal to 1 minus chi1, equation 1.2.3, that is this equation can be reduced to delta P1 is equal to chi2 P1 naught. We know that mole fractions add up to 1 for a particular molecule or a component, right? Now chi 1 minus chi1 can be represented as chi2, so we are taking as delta P1 is equal to chi2 P1 naught. In a solution containing several non-volatile solutes, the lowering of the vapor pressure depends on the sum of the mole fraction of different solutes. Equation 1.2.4, this equation can be written as delta P1 by P1 naught is equal to P1 naught minus P1 by P1 naught, which gives you chi2. Okay, now the expression on the left hand side of the equation, as mentioned earlier, is called relative lowering of vapor pressure. Now we are actually looking into the relative lowering of vapor pressure, that is, which is one of the colligative properties, right? Relative lowering of vapor pressure, because this is the reduction in the vapor pressure from pure form to solution form, which is relative to the vapor pressure in its pure form, will be equal to chi2. Chi2 is nothing but your mole fraction of the solute and is equal to the mole fraction of the solute. The above equation, this equation can be written as this left hand side has been taken. So P1 naught minus P1 by P1 naught is equal to, instead of chi2, they are expanding the mole fraction formula, N2 by N1 plus N2, since chi2 is equal to N2 by N1 plus N2. And here N1 and N2 are the number of moles of solvent and solute respectively present in the solution. Now for dilute solutions, the number of solute particles present will be much less than the number of solvent particles, and therefore N2 will be very much less than N1. Hence, neglecting N2 in the denominator, we have P1 naught minus P1 by P1 naught is equal to N2 by N1. This adding of N2 here will not affect, this adding of N2 in the denominator will not affect the, the value here, because N2 is much less than N1. So adding much less quantity to N1 will not bring a greater change in the formula. Therefore, we are neglecting N2, and so we are taking it as N2 by N1. Now expanding N2 and N1 itself, we will have N2 is nothing but number of moles of solute. Now number of moles of solute will be mass of solute, which is W2, or weight of solute W2, by molar mass of solute, that is capital M2, that is molar mass of solute. Now by N1, N1 is number of moles of solvent. Number of moles of solvent is nothing but weight of solvent particles by the molar mass of the solvent. Now when there is W2 by M2 by W1 by M1, then your W1 will go to the denominator and M1 will go to the numerator, forming this equation now here. Now this equation will be used as a formula for finding the relative lowering of vapor pressure of any solution. So the formula would be P1 naught minus P1 by P1 naught is equal to W2 into M1 by M2 into W2. To remember this W2, M2, all these might be confusing, right? So remember that W2 by M2 into M1 by W2. So W2 will be on the numerator and W1 will be on the denominator. M1 will be on the numerator and M2 will be on the denominator. Here W1 and W2 are the masses and M1 and M2 are the molar masses of the solvent and solute respectively. From this equation 1.28, this equation, knowing all other quantities, the molar mass of solute M2 can be calculated. So this will be your numerical question where they'll give you P1 not P1, then W2, M1, W1, everything they'll be giving, and you will have to find M2. Now to find M2, you can just bring M2 this side and these quantities to the other side, and you can calculate the M2 part. This example is based on this formula. So this example is based on this formula. Now moving ahead with the second colligative property, elevation of boiling point. The vapor pressure of a liquid increases with increase of temperature. It boils at the temperature at which its vapor pressure is equal to the atmospheric pressure. For example, water boils at 373.15 Kelvin, because at this temperature the vapor pressure of water is 1.013 bar, which is 1 atmosphere. We have also learned in the last section that vapor pressure of the solvent decreases in the presence of non-volatile solute. Figure 1.7 depicts the variation of vapor pressure of pure solvent and solution as a function of temperature. For example, the vapor pressure of an aqueous solution of sucrose is less than 1.013 bar at 373.15 Kelvin. In order to make this solution boil, its vapor pressure must be increased to 1.013 bar by raising the temperature above the boiling temperature of the pure solvent water. Thus, the boiling point of a solution is always higher than that of the boiling point of the pure solvent in which the solution is prepared, as shown in figure 1.7. Similar to lowering of vapor pressure, the elevation of boiling point also depends on the number of solute molecules rather than their nature. Now, let us look into what this elevation of boiling point is basically. So, what they are trying to say is, in the vapor pressure of a liquid increases with increase of temperature. Okay, and the liquid basically boils at the temperature at which its vapor pressure is equal to the atmospheric pressure. That is, what is the boiling point? Boiling point of a liquid is nothing but the temperature at which its vapor pressure is equal to the atmospheric pressure. They might ask what is boiling point in your viva, or they might also ask in exams, right? So boiling point is nothing but the temperature at which its vapor pressure will be equal to the atmospheric pressure. Now water boils at 373.15 Kelvin. This is 100 degrees Celsius, because at this 100 degrees Celsius its vapor pressure is equal to the atmospheric pressure, which is nothing but 1 atmosphere or 1.013 bar. Now we have also learned that the vapor pressure of the solvent decreases in the presence of non-volatile solute. That is what we saw in relative lowering of vapor pressure also, and before that, before few sections back also we saw the same thing. Now the variation has been depicted in this picture relative as a function of temperature. Now, for example, the vapor pressure of an aqueous solution of sucrose is less than 1.013 bar at 373.15 Kelvin, because now the vapor pressure has reduced. Liquids, water's boiling point was 373.15 Kelvin. At that point, the vapor pressure was 1.013 bar, which is equal to the atmospheric pressure. But when there was sucrose added to the water, vapor pressure decreased, because we know relative lowering of vapor pressure, we know that vapor pressure of the solution would have decreased than it was for the water separately as a pure component. Now that the vapor pressure has decreased, the aqueous solution of sucrose cannot boil at the same temperature it used to boil when it was simply water. Now the solution has to match its vapor pressure along with the atmospheric pressure. Atmospheric pressure will always be 1.013 bar. So now vapor pressure also should be equal to that in order for the solution to boil. So for the solution to boil, the temperature has been increased, because we know that just now we saw vapor pressure increases with increase in temperature. So if you have to increase the vapor pressure, then you have to increase the temperature. Its vapor pressure must be increased by raising the temperature above the boiling temperature of the pure solvent. The pure solvent can boil at 373.15 Kelvin, but for the aqueous solution of sucrose and water to boil, we need to increase the temperature above this temperature in order to make the vapor pressure equal to the atmospheric pressure and for a solution to boil. Thus, the boiling point of a solution is always higher than that of the boiling point of the pure solvent. which is in which the solution is prepared as shown in figure 1.7. Similar to lowering, the elevation is also depends on the number of solute molecules. So that is why we consider this to be the colligative property. It depends only on the number of solute molecules present rather than their nature. A solution of 1 mole of sucrose in 1000 grams of water boils at 373.52 Kelvin at 1 atmospheric pressure. Now, let Tb naught be the boiling point of pure solvent. Tb naught is the boiling point of pure solvent, which is represented here. Then, Tb be the boiling point of the solution, which is here. The increase in the boiling point, nothing but delta Tb, that is how much increase there is been, is delta Tb is equal to Tb minus Tb naught, that is the greater temperature minus the lesser temperature, and this is known as the elevation of boiling point. So delta Tb is only your elevation of boiling point, which is Tb minus Tb naught. Here this graph represents vapor pressure as a function of temperature here. So this solvent will boil at this particular point when the vapor pressure and atmospheric pressure equalizes at this particular point. When the temperature is Tb naught, the solvent will boil, pure solvent. But when it has become a solution, that is when the solute is added to the solvent, now the vapor pressure has to match the atmospheric pressure. For that, the temperature has been increased from Tb naught to Tb, and now only the vapor pressure is equal to the atmospheric pressure, and it boils here. So this increase in temperature in order to make the solution to boil is nothing but your delta Tb, and since it is greater than the boiling point of the solvent, it is called as elevation of boiling point. Experiments have shown that for dilute solutions, the elevation of boiling point delta Tb is directly proportional to the molal concentration of the solute in the solution. Molal concentration is nothing but molality of the solute in the solution. So through experiments, they have found out that delta Tb is directly proportional to small m. Small m is molality, and to take away this proportionality sign, we are keeping this proportionality constant, that is Kb. Kb is nothing but your boiling point elevation constant. Here m is molality, is the number of moles of solute dissolved in 1 kg of solvent, and the constant of proportionality Kb is called boiling point elevation constant or molal elevation constant or biblioscopic constant. Now they might also ask as a 1 mark question that what are the other names for Kb, or they might give biblioscopic constant and they may add what it is. It is the boiling point elevation constant. Okay, the unit of Kb is Kelvin kg mole inverse. Values of Kb for some common solvents are given in table 1.3. Now where is the 1.3? Okay, let's see that later. Now if W2 gram of solute of molar mass M2 is dissolved in W1 gram of solvent, then molality M of the solution is given by the expression M will be number of moles of solute. So that is nothing but W2 by M2 and by W1 by 1000, where they are representing it in kg, right? So now when you rearrange this 1000 into W2 by M2 into W1, substituting the value of molality in this equation, delta Tb, which is the elevation of boiling point, is equal to Kb into 1000 into W2 by M2 by W1. Now if you want to find the molar mass of the solute, that is M2, then just shift M2 here and delta Tb to the denominator. Thus, in order to determine M2, molar mass of the solute, known mass of solute in a known mass of solvent is taken, and delta Tb is determined experimentally for a known solvent whose Kb value is known. So when the values of Kb, delta Tb, W2 and W1 are known, then you can find the molar mass of the solute. To the third colligative property, depression of freezing point. As we saw, elevation of boiling point, similarly both are similar concepts, except for there is an increase in the temperature above the boiling point, and so we call it as elevation of boiling point. Here there is a decrease in the temperature below the freezing point, so we are calling it as depression of freezing point. Let us read through the text. The lowering of vapor pressure of a solution causes a lowering of the freezing point compared to that of the pure solvent. We know that at the freezing point of a substance, the solid phase is in dynamic equilibrium with the liquid phase. What is the freezing point? at the freezing point of a substance, solid phase is in dynamic equilibrium with the liquid phase. Thus, the freezing point of a substance may be defined as a temperature at which vapor pressure of the substance in its liquid phase is equal to its vapor pressure in the solid phase. So, what is freezing point? Define freezing point. It can be defined as the temperature at which vapor pressure of the substance in its liquid phase is equal to the vapor pressure in the solid phase, because the solid phase and liquid phase are in the dynamic equilibrium. So their vapor pressure also will be equal at that point, at that particular temperature. We call that particular temperature to be freezing point, and at that particular temperature the liquid will freeze into the solid. A solution will freeze when its vapor pressure equals the vapor pressure of pure solid solvent, as is clear from figure 1.8. According to Raoult's law, when a non-volatile solid is added to the solvent, its vapor pressure decreases, and now it would become equal to that of solid solvent at lower temperature. Thus, the freezing point of the solvent decreases. So, generally we know that when a solid non-volatile solute is added to the solvent, its vapor pressure decreases. Now, this vapor pressure would become equal to that of the solid solvent at lower temperature. Thus, the freezing point of the solvent will decrease. See, the freezing point at which the liquid had to freeze would have been Tf naught, that is pure Tf naught is the freezing point of the pure solvent, and now when the solute is added, the vapor pressure would have already decreased, and that vapor pressure which is already decreased would become equal to the vapor pressure of the solid solvent, pure solid solvent at lower temperature itself. So when it is equalizing, they have said that the solution will freeze when its vapor pressure equals the vapor pressure of the pure solid solvent. And now when the vapor pressure of the solution has decreased on its own, it would become equal to the solid solvent, vapor pressure of the solid solvent, even at lower temperatures than it had to, like at temperatures lower than the freezing point, and that is why the freezing point of the solution decreases. Okay, now let Tf not be the freezing point of the pure solvent represented here. Tf be its freezing point when non-volatile solute is dissolved in it. The decrease in freezing point would be delta Tf. This is a decrease in freezing point, which is Tf naught minus Tf. Remember, delta Kf was Kf minus Kf naught, not Kf, sorry, it is delta Tb. Delta Tb is nothing but Tb minus Tb naught, whereas delta Tf is Tf naught minus Tf, is known as depression in freezing point. Similar to elevation of boiling point, depression of freezing point delta Tf for dilute solution is directly proportional to molality m of the solution. For dilute solutions, through experiment they have found that Tf naught again is directly proportional, delta Tf is directly proportional to molality, and they have added this proportionality constant Kf, which is nothing but freezing point depression constant or molal depression constant or constant. The unit of Kf is again Kelvin, kg, mole inverse, similar to Kb. Values of K for some common solvents are listed in table 1.3. If W2 gram of the solute having molar mass M2 present in W1 gram of solvent produces the depression in freezing point delta Tf of the solvent, then molality of the solute is given by this is all similar to elevation of boiling point, except for the concept that for a boiling point there is an increase in the temperature, so we are calling it as elevation. For freezing point, there is a decrease in the temperature for the solution than the solvent, so we are calling it as depression of the freezing point. Now molality is W2 by M2 by W1 by 1000. Substituting this value of molality in the equation 1.34, this is 1.34, we get delta Tf value. Now delta Tf is nothing but Kf into W2 into 1000 by M2 into W1. Rearranging all these values, we get this. And if you want to find the molar mass of the solute, then rearrange M2 to this side and bring delta Tf to the denominator, and you will get the value. Thus, for determining the molar mass of the solute, we should know that quantities W1, W2, delta Tf along with the molar freezing point depression constant. The values of Kf and Kb, which depend upon the nature of the solvent, can be ascertained from the following relations. So Kf and Kb formulas are given. Generally in the numericals, the value of Kf and Kb will be given. They might not ask you to find it through this formula, but they might ask this formula in a 1 mark question, or in a match the following, or in MCQ, whatever it might be. So it is good to know this formula, right? Kf is R into M1 into Tf square by 1000 into delta H fusion. Similarly for Kb, R into M1 into R into M1 into Tb square by 1000 into delta H vaporization. Here the symbols R and M1 stand for the gas constant. R is gas constant, M1 is the molar mass of the solvent, and respectively Tf and Tb are freezing point and boiling point of pure solvent in Kelvin. And further, delta H fusion and delta H vaporization represent the enthalpies for fusion and vaporization of the solvent respectively. Now they have given the values of Kb and Kf in this table 1.3 here for few of the solvents. Coming to the fourth colligative property, osmosis and osmotic pressure. Osmotic pressure is a colligative property, and we will also be learning about osmosis here. There are many phenomena which we observe in nature or at home. For example, raw mangoes shrivel when picked in brine. Brine is nothing but salt water. Wilted flowers revine when placed in fresh water. Blood cells collapse when suspended in saline water, etc. If we look into these processes, we find one thing common in all, that is all these substances are bound by membranes. These membranes can be of animal or vegetable origin, and these occur naturally, such as pig's bladder or parchment, or can be synthetic, such as cellophane. These membranes appear to be continuous sheets or films, yet they contain a network of submicroscopic holes or pores. Small solvent molecules like water can pass through these holes, but the passage of bigger molecules like solute is hindered. Membranes having this kind of properties are known as semi-permeable membranes, SPM. Assume that only solvent molecules can pass through these semi-permeable membranes. If this membrane is placed between the solvent and solution, as shown in figure 1.9. So this light blue portion is the solvent space where it is a pure solvent, and this dark blue portion is representing solution, and this outline, black outline, is your semi-permeable membrane. Now they are keeping the semi-permeable membrane in between the solvent and the solution. The solvent molecules will flow through the membrane from pure solvent to the solution. Now when this membrane is placed between the solvent and solution, we know that this membrane will allow only solvent molecules. Then the solvent molecules will flow through the membrane from pure solvent to the solution. This process of flow of solvent is called as your osmosis, because the concentration of solvent in the solvent space is higher than that of the solution, because solution contains solute also. So the concentration of solvent will be lesser in solution than in the solvent space. So your solvent from solvent space will move to the solution space through the semi-permeable membrane. From higher concentration to lower concentration. Higher concentration of solvent is present in the solvent space, and lower concentration of solvent in the solution space. So from higher concentration, the solvent molecules will move to the solution through the semi-permeable membrane. This process of flow of solvent is called osmosis. The flow will continue till the equilibrium is attained. The flow of the solvent from its side, so solvent space, right? The flow of solvent from its side to the solution side across a semi-permeable membrane can be stopped if some extra pressure is applied on the solution. Now the flow of solvent from solvent side to solution is natural through the semi-permeable membrane. If you want to stop that, then we need to apply a pressure in the solution side in order to stop the solvent from being flown from the solvent side to the solution. This pressure that just stops the flow of solvent is called osmotic pressure of the solution. The flow of solvent from dilute solution to the concentrated solution across a semi-permeable membrane is due to osmosis. That is, these are all the definitions for osmosis, right? One could be flow of solvent is called osmosis. Other could be flow of solvent from its side to solution side across a semi-permeable membrane is also called as osmosis, or the flow of solvent from dilute solution to the concentrated solution across a semi-permeable membrane is also osmosis. And this semi-permeable membrane word is very very important. The important point to be kept in mind is that solvent molecules always flow from lower concentration to higher concentration of solution. I mean, see, I told you higher concentration to lower concentration. I meant that higher concentration of solvent in that particular area to lower concentration of solvent in that particular area. So I meant that solution will have low concentrations of solvent here. So do not get confused. Now we'll learn from this itself. Lower concentration, they mean is dilute, to higher concentration here is concentrated solution. They mean here all about solution, and I meant about solvent. Do not get confused. So there are three definitions for osmosis, as I told you: from its side to solution side across semi-permeable membrane, or from dilute solution to concentrated solution across a semi-permeable membrane, or from lower concentration to higher concentration of solution through semi-permeable membrane. All these are osmosis. The osmotic pressure has been found to depend on the concentration of the solution. The osmotic pressure of a solution is the excess pressure that must be applied to the solution to prevent osmosis. This is the definition for osmotic pressure. This pressure that just stops the flow of solvent is called osmotic pressure. That is, a pressure of a solution is the excess pressure that is applied to a solution to prevent osmosis. That is to stop the passage of solvent molecules through a semi-permeable membrane into the solution. Now this is illustrated in figure 1.10. Osmotic pressure is a colligative property as it depends on the number of solute molecules and not on their identity. For dilute solution, it has been found experimentally that osmotic pressure is proportional to the molarity C of the solution at a given temperature T. That is, pi is the osmotic pressure. Pi represents osmotic pressure, which is equal to CRT, where C is the molarity of the solution, T is the temperature, and R is your gas constant. Now molarity can be expanded into its formula, that is N2 by volume, number of moles of solute by volume of solution in liters, into RT. Here V is volume of a solution in liters containing N2 moles of solute. If W2 grams of solute of molar mass M2 is present in the solution, then N2, that is number of moles of solute, will be equal to mass W2 by molar mass of solute M2. And we can write osmotic pressure into volume will be equal to W2 RT by M2, where your volume has come from this side's denominator to the other side. Now if you want to get the molar mass of the solute, then bring molar mass to the other side and bring osmotic pressure and volume to the denominator. Now the formula would be M2 is equal to W2 RT by osmotic pressure into volume. This would be the formula frequently asked in your numericals. That is, they'll generally ask you, if it is a simple numerical, then generally you'll be asked to find the molar mass of the solute. You will have to know the formula, and these values will be given. From that you will be calculating the molar mass. Now thus, knowing the quantities W2, T, pi and V, we can calculate the molar mass of the solute. Measurement of osmotic pressure provides another method of determining molar masses of solutes. Like how we saw that through the relative lowering of vapor pressure we can find the molar mass. Similarly, by the expression of elevation of boiling point and through the expression of depression of freezing point, we can find the molar mass of the solute. Similarly, we have got another method, that is finding the osmotic pressure method. That method will provide another way to determine the molar mass of the solute. Now this method is widely used to determine molar masses of proteins, polymers and other macromolecules. Why so? That the reasons are being provided here. So the first reason is osmotic pressure method has the advantage over other methods. The first reason being pressure measurement is around the room temperature and the molarity of the solution is used instead of molality. So temperature is around the room temperature. There is no need of increasing the temperature or decreasing the temperature. And also, as compared to other colligative properties, its magnitude is large even for very light dilute solutions. So easier calculations can be made if it is having a little larger magnitude than the other colligative properties. Then the technique of osmotic pressure for determination of molar mass of solutes is particularly useful for biomolecules, as they have said proteins, polymers and other macromolecules, as they are generally not stable at higher temperatures and polymers have poor solubility. So using of osmotic pressure method to determine the molar mass of biomolecules is very helpful, because biomolecules at higher temperatures are not stable and they get denatured, or their structures are denatured at higher temperatures and pressure. But since that osmotic pressure does not need higher temperature, and it can be measured in the room temperature itself, it is used to measure the determine the molar mass of the biomolecules and polymers. Now, two solutions having same osmotic pressure at a given temperature are called isotonic solutions. They might ask the definition for isotonic solution. Also, this isotonic solution is a frequently asked numerical question where they might give you that two solutions are isotonic. That means that you need to compare the osmotic pressure of both the solutions. That is, you need to equate the osmotic pressures of the first solution to the second solution. That is why they have mentioned that it is isotonic solution. So the definition would be having same osmotic pressure are at the given temperature is very important, are called isotonic solutions. When such solutions are separated by semi-permeable membrane, no osmosis occurs between them. Since they have both the solutions have osmotic pressure, when they are separated by a semi-permeable membrane, there will not be any osmosis, because the pressure on both the sides are equal, so there won't be any flow of solvent from one side to another side. For example, the osmotic pressure associated with the fluid inside the blood cell is equivalent to that of 0.9% mass by volume of the sodium chloride solution called normal saline solution, and it is safe to inject intravenously. On the other hand, if we place the cells in a solution containing more than 0.9% mass by volume sodium chloride, water will flow out of the cells and they would shrink. Such a solution is called hypertonic. If the salt concentration is less than 0.9%, the solution is said to be hypotonic. In this case, water will flow into the cells if placed in this solution, and they would swell. So what does it mean? The fluid in the blood cell and 0.9% sodium chloride solution are isotonic solutions. That is, they have the same osmotic pressure. Therefore, that is, the sodium chloride solution is nothing but normal saline solution. So this saline solution and blood cell fluid are having the same osmotic pressure, and so they are isotonic. So they can be injected intravenously, that is directly into the veins they can be injected, because there won't be any pressure difference and there won't be any flow of solvent from one side to the other side. Whereas if the blood cells are placed in a solution containing more than 0.9% mass by volume, then water will flow out of the cells and they would shrink. That is, we know that solvent would flow from lower concentration to higher concentration, that is from dilute side to the concentrated side, right? Now this solution containing more than 0.9% is concentrated, whereas our blood cell is having 0.9% mass by volume. So now the water will flow out of the cells, that is from the cells it will move out to the solution, that is your saline solution, making the cells to shrink. Now such a solution is called hypertonic. Hypertonic solutions are those which are concentrated than the cells, and if the salt concentration is less than 0.9%, then it is dilute than the blood cells. So the solution, this kind of solution is called a hypotonic. Hypo means less than 0.9% and hyper means more than 0.9%. Okay, in this case water will flow into the cells if placed in the solution and they would swell, because now water is more concentrated than your hypotonic solution right here. So the solvent would move out from the hypotonic solution to the cells, in thereby making the cells swollen. Now the phenomena mentioned in the beginning of this section can be explained on the basis of osmosis. A raw mango placed in concentrated salt solution loses water via osmosis and shrivel into pickle. Wilted flowers revive when placed in fresh water. A carrot that has become limp because of water loss into the atmosphere can be placed into the water, making it firm once again. Water will move into its cells through osmosis. When placed in water containing less than 0.9%, blood cells swell due to flow of water in them by osmosis. People taking a lot of salt or salty food experience water retention in tissue cells and intercellular spaces because of osmosis. The resulting puffiness or swelling is called edema. Now this might be an important question where they might ask what is the reason for edema, or what is the puffiness or swelling caused due to, intracellular spaces of because of osmosis. Anything about this point could be asked. Okay, so people taking a lot of salt or a salty food experience water retention in tissues. Water movement from soil into plant roots and subsequently into upper portion of the plant is partly due to osmosis. The preservation of meat by salting and of fruits by adding sugar protects against bacterial action. Through the process of osmosis, a bacterium on salted meat or candied fruit loses water, shrivels and dies. So these are the examples provided for osmosis, where they have stated both about hypertonic and hypotonic. That is, they have given examples for both, you know retention of water or movement of water from one system to another side. Now we will talk about reverse osmosis and water purification. Reverse osmosis, that we would have heard many times, RO, that is reverse osmosis. The direction of osmosis can be reversed if a pressure larger than the osmotic pressure is applied to the solution side. That is, now the pure solvent flows out of the solution through the semi-permeable membrane. This phenomenon is called reverse osmosis and is of great practical utility. So we know that osmosis is nothing but flow of solvent from its side to the solution, that is from lower concentration to higher concentration, or from dilute side to concentrated side, these through a semi permeable membrane. Now this is generally osmosis, but if you want to reverse this osmosis, that is make the solvent flow from the solution side to the solvent side, or from higher concentration to lower concentration, or from concentrated solution to dilute solution, these are all not generally happening. That is, this is not naturally going to happen. So for this we will apply an extra pressure that is larger than the osmotic pressure in order to reverse the direction of osmosis, and this phenomenon is called reverse osmosis. Now reverse osmosis is used in desalination of of seawater. A schematic setup for the process is shown in figure 1.11. Now this is your schematic setup of desalination of seawater. This is your fresh water here, salt water here. Pressure given here is greater than your osmotic pressure. So when the pressure is equal to your osmotic pressure, what will happen? That is, when the pressure is left undisturbed, this will be equivalent to the osmotic pressure. Then what will happen? From the side of the fresh water, the solvent will be moving to the side of the salt water. But now we want the solvent present in the salt water to move from this side to the freshwater side in order to desalinate the seawater or purify the seawater. For that purpose, we are giving through the piston, with the help of the piston, we are applying a pressure greater than the osmotic pressure. So what will happen? There will be a reverse in the direction of osmosis, and solvent from saltwater side through the semi-permeable membrane will be going to the freshwater side, and we are having this water outlet. From there we can we can take the fresh water for our usage. Okay. When pressure more than osmotic pressure is applied, pure water is squeezed out of the seawater through the membrane. A variety of polymer membranes are available for this purpose. The pressure required for the reverse osmosis is quite high. A workable porous membrane is a film of cellulose acetate placed over a suitable support. Cellulose acetate is permeable to water but impermeable to impurities and ions present in seawater. These days, many countries use desalination plants to meet their potable water requirements, and this was one of the viva questions that I got when I had my practicals. The cellulose acetate is permeable to water but impermeable to impurities and ions present in seawater. So they might ask which was a workable porous membrane that is suitable for reverse osmosis, and it prevents the impurities and ions in the seawater. Then it is cellulose acetate. With this, we have come to the end of this video. Thank you for watching. If you found this video helpful, please like and subscribe for more educational content. Don't forget to hit the notification bell so you never miss an update. Your support helps us create more valuable resources for learners like you. Keep exploring and stay curious. Bye.